Hello, welcome to this AQA Further Maths Statistics video, the third in the series Errors in Tests 2, and this time we're going to be looking at type 2 errors for other discrete distributions. So just a quick reminder again that a type 2 error is involving incorrectly accepting H0. So we're interested in what happens to accept a null hypothesis, and it can be thought of as a false negative because although in fact there has been a change and H0 is incorrect, we haven't detected that, so we've simply concluded accept H0. So it's the probability of accepting H0 when H0 is false, and if you recall from the previous video, that means that you will need to be given more information about the actual population parameter involved. So they will need to tell you, in fact, it is actually a particular value, and then you can use that when you're trying to find the probability of a type 2 error, and remember we denote that beta. So if we look at an example here using a binomial model, and you may well want to pause here and just read through this scenario and work out your binomial model and work out the hypothesis test that needs to be carried out. So clearly it's a test on a proportion. We're investigating whether it's greater than the existing value of a 0.7, so that would be our initial null hypothesis. Is it 0.7 or greater? We have a sample of 14 customers, so that's giving us the n in our binomial model. It's a 5% test, and again remember we're looking at a greater than, so a one-tail alternative hypothesis, and we need to find the probability of making a type 2 error. And here's our additional information. If in fact we knew the population proportion preferring the new site actually isn't 0.7 anymore, it's 0.8. So these are our hypotheses, very simple to write those down. It's a one-tail test. And what we need to do now is to think about just the initial test here that we would do, and think about the range of values that would lead us to reject the null hypothesis, and therefore identify those range of values that would lead us to accept the null hypothesis. So one-tail test, we're only looking at the top end. Our model obviously is binomial, so x is the number of customers preferring the new site, and that would be modeled by a binomial distribution where n is 14 and p is 0.7. So in this case we're just looking at this initial test, so we'd assume 0.7 is the correct value. And if you just check on your calculator, you'll find for this 5% test the extremely unlikely top tail that just keeps us under our 5% significance level for this one-tailed test is greater than or equal to 13 people out of 14 preferring the new site. So these values are our critical values, it's our critical region, and those are the outcomes that would lead to us rejecting the null hypothesis. And that's just illustrated here for you with the probabilities of all the outcomes possible. And our rejection would be, to keep it below 5%, 13 or 14 people saying they preferred the new site. Clearly, if we went down to 12, that's way above our 5%, so we can't go down any further. So we know then we will accept the null hypothesis here if we get between 0 and 12 out of our 14 preferring the new site, but extremely we will reject our null hypothesis if we get 13 or 14 preferring the new site. So let's just look at all the information so far. We know the critical region to reject H0 is 13 or 14, and of course that then tells me that the event accepting H0 involves getting the outcomes 0 to 12. And we need to work out that probability with the actual now true value for P being given to us as 0.8. So it might look a bit complicated, but hopefully you can see what's going on. We need to accept, which means we need the outcome 0 to 12 in favour out of our 14 in the sample, given that H0 is false, so using our new value for P. So simply, what's the probability we get between 0 and 12 from a sample of 14 when P is actually 0.7, it's 0.8. And that comes to 0.8021 directly off the calculator, and so that's the probability of our type 2 error for this particular hypothesis test. So if we now look at an example from a Poisson model, and again perhaps you want to just pause here and read through and work out the information you've been given and how the test would be set up for this particular scenario. We're told we're modelling with a Poisson distribution, and we're given the initial value for our Poisson mean as 4.5, because that's what's been going on in the past. So we're now having a new maintenance schedule. We're counting the number of breakdowns in the month following, and we're going to carry out a test at 10% to see whether the mean number of breakdowns has changed. And the demand for this particular scenario is to find the probability of a type 2 error if, in fact, with the new schedule, lambda was equal to 6.5. So this is our extra bit of information we'll need to use when we are working out the probability of a type 2 error. So setting it up, it's clearly a two-tailed test. Again, we need to find when we would accept H0. So we need to find the rejection, the critical values, and we need to then work out what range of outcomes could happen for the number of breakdowns occurring in the month following the start of the new schedule that would lead us to decide that we'd accept H0. So we have a two-tailed test. It's a two-tailed test at 10%. And initially we are modelling the number of breakdowns with a Poisson distribution with mean 4.5. We're assuming our null hypothesis is true. And we're looking for the extreme values each end, and remember we need to be less than or equal to 5% at each end. This is a test at 10%. It's two-tail, so we always split our significance 5% or less at the low and 5% or less at the high end. And this actually gives us, again, you can check on your calculator, only 0 in fact at the low end, otherwise the probability is too large, and 9 or more at the top end for this two-tailed 10% test. And this is illustrated here for you. You can see all the different probabilities on the right, and here we are going to reject at the low end if we get just 0. You can see the probability of getting 1 is actually over 5%, so that's pushing our probability above the 5% or less that we need at the low end. And in order to keep our probability at 5% or less at the top end, it's 9 or more. If we include 8, that's going to be far too big, so it's 9 or more at the top end, and the cumulative probability of that 0.0403, which is below our 5%. So where we've got to is we know where we're going to reject at 0 or 9 or more breakdowns in the month following the new schedule, but if we want to work out the probability of a type 2 error, we need to find the probability we accept the null hypothesis. So obviously that's going to be the opposite of this. It's going to be getting the outcome 1 to 8, and of course we use our new bit of information that actually the population mean has changed to 6.5. So we want to accept H0 when H0 is false, and in fact lambda is 6.5. So again, simply on your calculator, it's the probability of getting a value of x between 1 and 8, and you might prefer to use your tables for Poisson, but using lambda equals 6.5, and you should obtain 0.79, and that's the probability of the type 2 error for this test. And that concludes this video.